Okay, lesson number 4 is just an extension of lesson number 3. We're going to continue on with permutations, but we're going to talk about distinguishable permutations. Targets, I can count the number of distinguishable permutations, and then I can apply distinguishable permutations to solve problems. So let's talk about what actually is a distinguishable permutation. If you remember, in lesson number 3, we looked at the number of different permutations for the letters A, B, and C. All right, so let's try that again. It says, how many distinct ways are there to order the letters of the word mom? So I have M-O-M, just like it's written. I could have O-M-M, and I believe I could have M-M-O, but I don't think I can come up with any more. All right. If you remember when we did A, B, and C, we actually came up with 6 different possibilities. This time we only came up with 3, and of course we know the problem is that I have an M here and an M here. So if I just simply switch them, it doesn't really look any different. It still looks like mom. So that's what we're talking about when we talk about distinguishable permutations. No longer can I just take 3 factorial, because that would get me 6, and here I really only have 3. So what happens when pieces are repeated and look the same? So here's our rule. The number of distinguishable permutations where one object is repeated q times, another is q2 times, and so on would be n factorial. So the number of letters you have, so in our case it would be 3 factorial, because I have 3 letters, and then what object is repeated? So I have an M, and an M is repeated twice, so I would divide by 2 factorial. I don't have anything else that's repeated. If I did, I would put another factorial underneath, but that's it. So we know 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. We can see that comes out to be 3, and so I was verifying that for the example above. So here's how it works. Let's try it on some words with some letters here. So Ohio has 4 letters. So permutations, normally I would do 4 factorial, but I see I have an O that repeats, and an O repeats twice, so I divide by 2 factorial, and that just comes out to be 12. Mississippi, if we count up, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. So that's 11 factorial. But I believe I have a lot of repeats. Like, let's look at the I's. I have 1, 2, 3, 4 I's. So I'd have to divide by 4 factorial. Then I also have S's. I have 1, 2, 3, 4 S's, so that's another 4 factorial. And then I also have 2 P's. So there is a 2 factorial. If you multiply that out, that's 34,650. So you are dividing by the repeated pieces. There were 4 I's, 4 S's, and 2 P's. All right, here are a couple applications of it, and then you'll get started on the work. You start at the lower left box, and you can only move up and to the right to get to this end box. It says, in how many different ways can you get to the upper right box? So the question is, how is this really a permutation problem? Well, if you think about it, to get from start to end, it says you can only move up and right. Well, up. Ultimately, no matter where you move up, you're going to have to move up 1, 2, 3, 4 boxes. So you're going to have to move up 4 times, right? To get from start to end, ultimately you're going to have to go to the right 1, 2, 3, 4, 5 times. Even if you did it down here, 1, 2, 3, 4, 5. Even if you went up, you'd have to go right once. Up, you'd go right twice. Up, you'd go right 3 times. Up, you'd go right 4 times, right? So either way, you're going to have to go to the right 1, 2, 3, 4, 5 times. Again, 1, 2, 3, 4, 5 times before you'd hit that end box. So you have to have some combination of moving up 4 times and right 5 times, right? Doesn't matter what combination you do it in. I could go up, right twice, up, right twice, up, right, up. Doesn't matter. But you can see now where this becomes a permutation, because I have to, I have 4 and 5, so that's actually 9 factorial, right? But here's where the distinguishable piece comes in. I have 4 ups and I have 5 rights, so I would divide by those. And you could do that on your calculator. That would get you your answer. All right, so there's an application of a distinguishable permutation. Now here's one more application. You want to form numbers that are 10 digits long. How many of these numbers contain 5 4s, 3 6s, and 2 8s? So there's our 10 digits, right? We have 4, 5, 6, 7, 8, 9. Did I miss something? Oh, 5 4s. Sorry, there we go. There's my 10 digits. All right, so here's one example of a number that would meet that category right there. I need a 10-digit long number that has 5 4s, 3 6s, and 2 8s. So there are 10 spots there. That's 10 factorial. But if I just switch these 2 4s, is that going to make a new number? Nope. So I would have to divide, since there are 5 of these, I'd have to divide by 5 factorial. And since there are 3 of these, I'd have to divide by 3 factorial. And since there are 2 8s, I'd also have to divide by 2 factorial. So it's the number of permutations of these numbers, but it's distinguishable because you have these repeating.